So we'll get started. Thank you all for coming tonight. I'm Shana Brogan, the Conservation Agent for the town of Eastham. And tonight we're going to hear about some interesting and very important topics that will be helpful for some of our regulatory board members that are here tonight as we receive new applications and issue new permits for things and activities in Eastham. Some of the projects that we are working on here in Eastham related to these topics include a harbor and waterways plan. We are restoring the connection between Great Pond and Deborah's Pond. We have an Outer Cape Shoreline Management Framework. We are assessing some of our low-lying roadways, and we are working with Outer Cape towns to develop regulations related to land subject to coastal storm flowage. So with that, I will turn it over to Greg Berman of the Woods Hole Group and Cape Cod Cooperative Extension.
So yeah, thanks for braving the rainy weather to come out. If I stray too far from the mic or something, just give me a heads up. So we're here to talk about sea level rise, erosion, and coastal processes in general. And I'm with the Sea Grant program at Woods Hole Oceanographic Institution down in Falmouth, and also Barnstable County, the Cooperative Extension. So we're going to start off with sea level rise. Basically, here's what's coming. But we have to think about timescales. This is an image that was created maybe a decade ago by URI, and they said, what if all the ice melted on Earth to try to figure out the overall sea level increase that would be? They're not saying that's happening this year or next year or within the next 100 years, but you see these images a lot for the shock value. For a while, there was a lot of emphasis on trying to shock people into action, to adapt, to mitigate. Unfortunately, a lot of the social science shows that when you show these images, it shocks people into inaction. At that point, they say, forget it, it's not worth doing anything about, it's too bad. So we're going to get into what the actual science is. In addition to the shocking images, there's also the emotional images of the charismatic macrofauna. But we need to look at the scale, right? So we're not telling a mistruth saying that the water has been that high. It has been that high. But we're talking, you can't see, 100 million years ago, 500 million years ago. These are very, very long time scales. At this point, we have plate tectonics in action, right? So, I mean, Cape Cod was not here. Cape Cod's relatively new. That was material brought down by the glaciers, and we'll talk about that a little bit. But these are different temporal scales. You have everything that I'll be talking about is really just, you can't even distinguish that line on the end when you're looking at these kind of time scales. So we're talking about sea level rise. There's various ways of measuring sea level rise. Basically, we still use tide gauges, and there's one down at Woods Hole. There's another one up in Boston. There's some on the islands. And those are the permanent stations. There's been some temporary ones, and there's offsets to be able to tell you like what the tide's going to be every day. But really, back in the 90s, we switched over to satellite altimetry. And so this actually sends a pulse out from space and measures the general elevation of the sea. And you get much broader coverage and much higher data density, much more accurate than just a series of tide gauges around. But there's a lot of correlation between those two that shows that it's quite accurate. When we're looking at the causes of sea level rise, there's a variety of things that can cause it. We're looking at thermal expansion. Right, so just an increase in temperature. When things get hotter, kind of from chemistry, there's more space between the molecules, and it expands, gets bigger. Same thing with the ocean. As you increase the temperature, the ocean's actually getting bigger. Melting land ice. So ice up on the land is going to melt, move its way down the streams and rivers to the ocean, raising the global sea level. There's also some other things up here, subsidence, local land subsidence, whether it's extraction of natural resources, whether it's groundwater pumping, you can affect things quite a bit. And also the overall terrestrial storage of water on land, that can affect the overall global water levels. These tend to be much more localized effects. In fact, when we're looking at global sea level rise, the two primary ones are thermal expansion and melting of land ice. And for a long time, the thermal expansion was the dominant one. But really, for the past 15 or 20 years, the melting of land ice has taken over. So if you add that blue and red together, you get purple. And this is the satellite altimetry elevation data, and we can see that the purple matches it because it's these two added together. We didn't even add in this other stuff, and you get fairly accurate correlation between the measured and observed that way. But we care about what's happening locally, right? So global sea level is one thing, regional and local sea level is something else. What we had 20,000 years ago and many times before that were glaciers, huge chunks of ice flowing down from the north. This ice had so much weight it could actually press down on the Earth's crust and lower the land itself. So this kind of crude image up here, you can see the ice is pushing down on the land. After that ice melts, it allows the land to come back up, called isostatic rebound, glacial rebound. You may have heard some of those terms, but it's after the ice goes away, the land's able to come back up. Now, to make it a little bit more complicated than that, it's not just the land coming back up, but there's actually a gravitational pull of the ice, right? So as this ice is less, the water is able to relax away from that shoreline. Now, it might be a little counterintuitive. How can anything actually pull water towards it like that? You have to think about the scale, right? So when we think about our daily tides, that's predominantly the sun and the moon driven. It's almost entirely the moon, just a little bit of the sun. The sun is much, much more massive than the moon, but the moon is much closer. Distance has a very big impact on that equation. Now, same thing with the glacier. It's much less massive than the moon, but it's right there next to the water, so it allows a certain amount of attraction and pull. What that means is, based on what ice sheet is melting at any given point in time, it could have more or less effect on our particular region. So when you hear about the Greenland ice sheet, as that melts, it adds water to the global system, but it allows water to flow away from the northern hemisphere down to the south. So it's not as bad. So even though global sea level might rise, it's not going to rise as much in our area. On the other hand, the West Antarctic ice sheet, as that melts, it puts water in the global ocean, and it allows water to flow away from the South Pole to the north. So it's kind of a double whammy when that one melts for the U.S. Northeast. Now, this last glacial period I talked about certainly wasn't the first. We have many, many glacial periods. And again, we always have to talk about what time scales we're looking at. That last graph had millions of years. This is merely thousands of years. And this is still a sea level rise graph. Here we are right here at present sea level rise. That's our last glacial maximum about 20,000 years ago. But it's gone up and down since that time. It's been higher, even just about 140,000 years ago. And this is how much land ice is taking water out of that global ocean. So about 20,000 years ago, we had significantly less water in the ocean, so the shoreline was much further offshore. About 15,000 years ago, all the ice on Cape Cod had melted. And what that means is it's adding water to the global ocean, but that doesn't mean that all the ice all the way back up to Canada had melted yet. So there's still a lot more melting going on over the next several thousand years. 11,000 years ago, you could have walked from Eastham all the way out to George's Bank. Kept your feet dry. So an entirely different regime back then. 6,000 years ago, we finally have George's Bank underwater, but you could have walked out to Nantucket. This is the time when erosion really started taking off for Cape Cod. So back here, you really only had wind and waves from this little area. Now you have full Atlantic fetch and swell potential. So you have storms coming from all the way across instead of just localized storm. This is when erosion of the kind of mid-outer Cape took off and material moved to the north and south. Provincetown wasn't even there 6,000 years ago. It's the material eroded from those glacial materials and moved to the north that formed the entire town. Same thing with Monomoy to the south. And then present day, obviously we have our continental shelf out here, which is where it used to be, and our current configuration. Now, to make sea level even more complicated, we certainly had ice pushing down on the Earth's crust, which lowered it, but the Earth's crust isn't as sturdy or as stiff as you might think. It actually has a bit of a rubbery consistency, and the very scientific term for this is glacial bulge. That if you push down on the Earth's crust, you're going to go down in the middle, but you're actually going to get uplift on either side. What that means, here's our ice sheet pushing down, and you get a bulge up here, and then as that melts, this is able to isostatically rebound back up, but now this used to be up and it's going down. When we look at that in our region, Boston and Woods Hole have a fairly consistent sea level rate. So these are actual tide gauge stations, measured water level at tide gauges. Nantucket's a little bit steeper curve, right? And that's because the land is going down there faster than the land is going down here. The land is going down across Cape Cod at the same time sea level is rising. So that's not a good combination. But Nantucket had that bulge on it a little more recently, and it's going down a little bit faster than we are. Now Louisiana, that's actually going down about 3 feet per 100 years, so 3 times faster than we are. And a lot of that has to do with subsidence of the land, the natural resource extractions, the aligning of rivers, preventing sediment transport and deposition. And then Alaska, on the other hand, that's actually seeing sea level fall 3 feet per 100 years. So what's going on with that? And it's not all of Alaska. Certain parts of Alaska are. They had ice on it much more recently. So they're actually rebounding up, and they're rebounding up faster than sea level rise. So because it's going faster, it's actually seeing a relative sea level fall as that land goes up. We don't have that happy situation. So here's the difference between global and local. Here's our global sea level rise. It was about 0.56 feet over the last 100 years. And then our local observations are about 0.9 feet over the last 100 years. Difference of about 1/3 of a foot. And that 1/3 of a foot is the local land subsidence. So that's the land going down. And with any kind of global sea level rise projection, we have to add in that local land subsidence. On the plus side, while projections of global sea level kind of have that very steep curve going into the future, this is relatively steady. That's not increasing, certainly not on the same time scale as the land, ice, water interactions. This is just an example of a photograph taken in 1900 down in Woods Hole. And you can see an algal stain right around the mean high water. And then the same image about 100 years later, just about a foot of difference between those rocks. And that's very closely close to the tide gauge record, which is just in the same location. So what can the past tell us about the future? Now we're going to kind of work our way towards what the projections of sea level rise are going to be in the future. So sea level rise has risen faster in the past. There was that pulse of melt back when we had a lot of glaciers melting all at once. This is more than 6,000 years ago. We had 5 feet per 100 years. And then from there till about 2,000 years ago, we had about a foot of sea level rise per 100 years. That's about what we have now. But for the last 2,000 years, we've had a really reduced rate, only about 1/3 of a foot per 100 years, which is why it's concerning that the last 100 years, we're seeing rates that we haven't seen in the last 2,000 years. So this isn't going to be on the test, but I wanted to show you kind of how these global ensemble models get put together. So this is the Intergovernmental Panel on Climate Change. A lot of very good scientists all over the world get together to put these consensus documents and ensemble models together. But each one has a parameter, right? So this red is thermal expansion, and that used to be one of the dominant forces. Now it's land ice. And so you can see this adds with this, and that, and then you get your best guess, which is that dark black line, and then your potential uncertainty, which is that gray box. And then each one of these is a different scenario, and I'll talk what those scenarios are right now. So that was our global sea level rise projections. The state went and downscaled it to Massachusetts sea level rise. So they took the global numbers and put them into Massachusetts numbers. Very basically, this is almost completely land subsidence. right? So they took the global numbers and just added how much our land is going down in addition to that water going up. Kind of to make it a little more useful, instead of just 2100, now they're breaking it down by various closer time scales, 2025, 2050, so we can use that for different planning horizons. And within 5 years of this coming out, they actually came up with newer numbers. This isn't the newer numbers, this is just a closer look. So from here you have a range of about almost 7 feet, as low as less than 1 foot. But this has been updated already back in 2018. And this is when they switched from the best guess to a probabilistic projection. And this is something that can take a little while to explain, and feel free to ask questions. We have plenty of time at the end. But what you're looking at here is the best guess number. And if you are putting a best guess up there, you have a 50% chance of being wrong and a 50% chance of it being worse, 50% chance of it being better. So a lot of the coastal managers came together and said, 50-50 is not a great number. We need more certainty than that. So they came out with various probabilistic projections. So the least probability they were willing to entertain is 83%. So these numbers show that we are 83% certain it won't be worse than this. And what that means is, instead of our best guess of 4.2 feet, now we're 95% certain it won't be worse than 5 feet. It's just a different way of talking about it, different way of planning for it.
Is that 5 feet like from today, or from 5 years ago, or
2000.
from 2000?
Yeah. But yeah, that's a good question, because they go from 1990, they go from 2000, there's a variety of starting points. And they've been doing this so long, you can actually, see some of these trends. It's been decades since they've started doing this. And that's a good lead-in to this RCP number, the representative concentration pathway. We don't have to get into exactly what that is, but this 8.5 number, that pretty much means there's going to be a lot of greenhouse gas emissions, right? And that's the highest one the IPCC put out. It goes all the way down to like 4.5, and that's assuming that somehow we're going to be able to mitigate and not put out as much greenhouse gas. They used to score these scenarios based on the RCPs. Now they just use this 8.5 because it used to be called the worst case scenario. Now it's called business as usual, because that, the observed trend has been nailing this 8.5 for so long. Now they're saying, well, this is what it's been, so we're going to project that into the future. Some things to think about. And in some of these other numbers, it's just it obviously bumps up the number as you increase the certainty and do these probabilistics. Now, they also took away our historic trend. So the next 100 years, there are probably less than 1% of climate scientists saying that the next 100 years is going to be like the last 100 years. Very, very unlikely. But now we've moved to a maximum physically plausible. This is kind of approaching ludicrous speed, right? So this is that melting all the ice as fast as we can. But it has a lot to do with ice sheet dynamic imbalance. And we're looking at numbers now that this is 99.5% certain it won't be worse than 7.6 feet. And then here is 99.9% sure it won't be worse than 10 feet. So do we really need 0.05% extra certainty if it's an extra 3 feet? That's not for me to say, that's for what particular project you're looking for. But again, look at the scale of everything and look at the assumptions based on it. So if you have 0.4% additional probability and additional 3 feet, depending on the project, you may be looking at a different probabilistic projection that you would be kind of keying in on. But this is what a lot of numbers are quoted as. So you'll see, like in the paper, that sea level rise projected to be between 4 and 10 feet by 2100. Well, what do those numbers actually mean? What's the likelihood? We're not trying to shock people by saying it's going to be 10 feet. This, in my mind, is a good way to show that, this last, high level of uncertainty doesn't get you much, probabilistic-wise. And here's what it looks like in a graphical form. Each one of these shades of blue is a different probabilistic. And so we'll look at them over here by 2100 because they stretch out a little bit better. But this light blue is that 83% sure. And that dark blue up there that's 99.9% sure. And this is kind of the classic, hockey stick advance as it goes into the future. This green line is actually observed data. The blue is the projections moving into the future. And you can see the difference between these is very little in recent future. But moving into the further away, 2100, you get much more distance between them. So that's why it can be hard to plan and explain exactly how you're going to incorporate that. Yes?
And is this assuming that the amount of greenhouse gas emissions is going to remain what it is today, or is there any thought that it's going to increase?
This is definitely assuming that the greenhouse gases are increasing, and increasing at a similar rate to that they have been over the last 10, 20 years. So this is, and there's actually been some kind of more ivory tower theoretical type things that even if you cut off CO2, like took us back to the Middle Ages, there's a certain amount of permanence of CO2 or momentum of CO2 in the atmosphere. And even if you cut it off, you're still locked into a certain amount of warming and sea level rise. But it's certainly closer to this number than that number. So it does assume increases in CO2 based on previous history. So one of the ideas with probabilistic is, I like this quote, man would do nothing if he waited until he could do it so well no one could find fault. And basically the idea is, like, how certain do we have to be? People, play the stock market. They do a variety of things where they're looking at percentages and the probability. So at what probability does it encourage you to take action? And we're going to kind of move eventually into what the cost of action versus inaction is. So this image up here at the top, the black line is observed water levels from the Woods Hole tide gauge. So this is observations. We actually have measurements. This is about the last 100 years there. These little kind of rainbow of lines up here, this red line, that's the 100-year storm. And I'm going to use this kind of interchangeably, but the 100-year storm is not a 100-year storm. It's a 1% chance in any given year. So you could have like 2 or 3 years and have them. It's just you're rolling the dice each year to see how high of a storm you get. And then the 50-year storm, the 10-year storm moving its way down, the 10-year storm is a 10% chance in any given year. But here we had two that broke the 100-year storm, the 1938 and Hurricane Carol. Now the idea is sea level is rising. So what happens if we get the exact same water levels for the next 100 years as the last 100 years? So we're going to increase that water level by 3 feet, right? So we just bump that up 3 feet. Now we have 400-year storms. We're doubling the amount of storms at that level. Another thing that's very concerning is instead of a 10-year storm, now we're seeing this happening every year. So think of the worst storm that happened over the last 10 years. If that were to happen every year, we're going to see some really big changes in erosion around here. And just looking at this, 3 feet is pretty much plus or minus, depending on your probability. So you're at least 95% sure it won't be worse than that, but you're really not getting to 3 feet even as a chance until 2060, 2070, and that's only in the higher probability ranges. I'll talk some more about this in some later slides. Another way to think about the changing return period of flooding is if anybody has flood insurance, this is the background information that defines what your flood risk is. So these are FEMA flood insurance studies that are based on the 100-year floodplain, and we're going to zoom into Eastham, right along here, and we're going to pick out one of these transects. So a transect is like a slice through the data model, and we're going to see what those numbers are. So the 10% chance storm is 8.9. The 100%, or I'm sorry, the 1% or 100-year storm is 10.2, about a 1.3 foot difference between a 10% and a 1%. Now, even the smallest, only 83% sure, that's telling us about 2040 or 2050, we're going to start seeing this. So our 100-year storm is going to start happening much more frequently, or at least the water level of the 100-year storm is going to happen more frequently. In addition to that, we can also look at the 500-year, might be closer to the 50-year, and the 100-year closer to the 10-year. So just these water levels that we've been seeing only very rarely or occasionally are going to happen more often. When we're looking at recent past, we had some flooding back in January of 2018. This is in the town of Dennis, but an area that I hadn't seen flooded in 10 years. And we had a high tide surge of a little over 3 feet right at the high tide. There was some erosion and some damage. This wasn't the major erosion. That one actually happened in March. This is the January one. Now, the thing to think with this particular storm is we've had other fairly big storms recently, right? We had Hurricane Sandy back in 2012. We had a nor'easter shortly after that. And these were fairly high water levels. This max surge was 4.5 feet. This one was 4 feet. This one was only a little over 3 feet. But you need to think about what time of day they happened, what tide level, right? So at high tide, the surge was only 2.5 feet during Sandy. At high tide, we just kind of nailed it on that January storm. It was right at high tide when it hit its maximum surge, which is the difference between the predicted water level and the observed water level. In fact, it was so high at the Boston tide gauge, it broke the record. It is the new storm of record, highest water level measured at Boston tide gauge. It beat the storm of 1978 by 2 inches. Now, the thing that's really interesting about that is we have been measuring the water level in Boston since way before 1978, and we have observed the water level increase 4.5 inches during those 40 years. What that means is if both those storms happened the same year, the 1978 storm would have been a higher water level storm. So the new storm of record in Boston is only that because of sea level rise. It started off higher. It didn't have to go to high to beat the record. It was the March storms that really kind of put a hammer on the Cape in a lot of ways. We had a lot more wind, a lot more erosion associated with it. That January storm came and went. That March one stuck around for at least a week. Here's the hydrograph. So we're looking, there's our predicted, there's our actual, the difference is the surge. And it didn't go away for a week. We still had a foot or two of surge for a long, long time. What that means is a lot of the natural resource areas that have been kind of softened up during the January storms in the first couple of days in March were able to be eroded even more during that long period. A lot of high tides, a lot of wind and surge pushing through. And I think most of these are from Sandwich, but significant damage. I mean, we're seeing a lot of buildings torn down and uninhabitable afterwards. And this just had to do with the particular wind direction and how vulnerable they were already. So now we're going to get into a little bit about the overview of the latest data and maps and those sea level rise projections, the downscaled ones. That's on resilientma.org. That's the state climate office putting those out. A lot of municipal vulnerability preparedness programs use it. They're required to use it. And the idea I like to show, so this is The Onion. This is a satirical website. I like to point that out. Not everybody gets that. But I love this, that at least 79% of statistics are now alarming or sobering. And they are, right? So, I mean, we are seeing a lot of these graphs and numbers that are disturbing. And they may not be, as disturbing as not taking a careful look at them, but that doesn't mean we shouldn't take action, because even a little bit of this graph can cause a lot of damage. Yep.
You've showed this before. This was a few slides ago, right?
Yes, same one.
When I looked at it before, I noticed that we're a month away from 2020, right? And the actuals look way below where those 4 colored bars are. Is that Can I draw any conclusions from that, that those bars are too pessimistic, or is that not appropriate?
So these are based on 2000, so it's actually back there that the difference is. But we, that would be interesting. I should have the actual number on there to update that. It's not my graph. But yeah, it's fairly accurate. We have
Is that
seen.
a fair or unfair observation that those 4 bars for 2020 look very pessimistic compared to the actuals?
You know, I should put that on there because we are right about here. We're in that range. But honestly, that one's almost a gimme because they started off slow and ramp it up high. So it's hard to be very wrong early on, especially because this does go up and down quickly, right? You have a really rapid increase here and a really rapid, decrease afterwards. So any kind of short-term variability in there might overshadow the overall trend. But here you have a trend going up, and then it's that kind of steep curve or hockey stick. And even looking at the smallest probability, you're still seeing an increase greater than we've seen in the past. And that has a lot to do with CO2. I didn't really have time to throw the whole CO2 global warming thing into this, but CO2 is really closely correlated with global warming, and our CO2 rates are kind of through the roof right now. But we can chat afterwards about that if you want. I did show that one again because we're going to show this little spot over here again, and here's a spot in Eastham. This is the Cape Cod Commission Sea Level Rise Viewer. They have a coastal planning tool you can look at, and you can flood your friends and neighbors. So there's 1 foot of sea level rise, 2 feet of sea level rise, and these red lines are disconnected roads. So Shana mentioned that you guys are looking at low-lying roads. If you start, flooding certain roads, then all these areas might not be able to be evacuated during temporary storms, and during, a longer period of sea level rise might not be a viable access route. And then there's 3 feet of sea level rise. And you can kind of zoom in all around Eastham or whatever areas of interest. Actually, if you increment this all the way up to 5 or 6 feet of sea level rise, everything turns red. And that's because the rotary actually becomes compromised at that point. And so pretty much we're an island out here. So now I took way longer on sea level rise than I should have, and we're going to breeze through coastal processes. The idea of coastal processes is things change. We're a pile of sand and a bunch of other stuff deposited by the glaciers, and that stuff moves. This is the idea. There's not really too many coastal processes cartoons out there. I like to encourage and showcase. If you want to be really accurate, he shouldn't have had a hand back then, because 6,000 years ago Provincetown wasn't around. I did not call the paper about that. We'll let that one go. But here is about the maximum extent of the glaciers. And how do we know that? Well, it dropped moraines. And what moraines are is where the big stuff falls, right? So the glacier can come down so far until it gets so warm that it melts. When it melts, the big boulders and everything falls out. But the water from the melting glaciers is able to move the sand and clays and that sort of thing and form floodplains. The big stuff stays there. The boulders aren't moving. So that's why we have these moraine deposits that form the spine of the islands. That's why the islands have that configuration. Then it melted and receded and stalled for a while. And it stalled, and that's why the Elizabeth Islands have that configuration and relatively rocky, and the spine of the Cape up here. Now, there were various lobes and melt periods, but one of the things of interest is for a while we had ice up here that was melting, feeding fresh water into here. So Cape Cod Bay was actually a lake back then. It was a freshwater lake, about this time frame. And then we had some kind of breakthrough areas near the Pamet. That's why that's a little bit lower, Sapping Valley, changing the geography of that area. So those are kind of the long-term glacial impacts, and these are the short-term coastal processes that are always happening in the background, relatively short-term. And there's a lot of different ways for sediment to move, sediment being, rock, sand, anything that can be moved by the water or wind. Very basically, parallel to shore is called longshore current. The idea with that is If you put something in the way, like the Cape Cod Canal, you can have winners and losers, right? So the transport is in this direction, it fills up this area, and the area down here is not getting that material, and it's eroding relatively quickly. This is a jetty. This would be called a groin just on the beach. It's intended to slow down instead of stop the sediment, but it has the same idea. There's a depositional shadow downdrift. So here's a look at a study we did at Longshore Transport. Obviously, in embayments, it gets very complicated. Once you're out here on the outer Cape and get out of this area of divergence based on wind energy, it gets very simple. Pretty much everything from this point is moving to the north. When we start looking at these areas, we have areas of divergence. Everything here is moving this way, everything here is moving this way. So if you have material moving away from you in both directions, that's going to be an eroding hotspot. And that's material that erodes, goes onto the beach, and provides material for the beaches and dunes on either side. Moving a little bit further north, everything is just pretty much passing through Truro on its way up to Provincetown. There's a little bit of back and forth here. There's a point of divergence, and this breakwater messes with the longshore transport. But the next image is from a Google Earth engine. We actually have this on the Cape Cod Extension website for a variety of sites. But if you look at a particular mound of sand, you can actually follow it with your eye as it moves around Cape Cod. Longshore sediment transport is often called a river of sand because that's kind of what it looks like. But now that we have satellite images, we can really show how that sand is moving, and it's very consistent direction once you get this far north on the outer arm. Another direction, instead of parallel to shore, is perpendicular to shore, cross-shore transport. You'll often hear about a summer versus winter profile, especially out at like Coast Guard Beach. I've seen some really impressive vertical changes after storms. We've seen 5 vertical feet of recovery just in a few months after a storm. And it's not because it's, cold versus warm. It's because those steeper waves are going to erode more, and the gentle waves in the summer bring it back. And here's kind of just a look at that, is how it moves offshore during steeper waves, and then the summer it's able to move back on. And the dunes and beach itself are a dynamic system. That's one of the performance standards of them, is they need to be able to erode and provide material and then rebuild over time in order to form their function. So here's what it looks like. It doesn't necessarily care if there's a house in the way. This is a barrier beach system, so you get overwash fans flowing over the beach and then moving the entire beach back over time. Here's kind of an extreme example of that from down on the Gulf Coast. This is right before and after Hurricane Ivan. The green is area that's a higher elevation after the storm. The red is an area that's a lower elevation after the storm. Any guesses what these red squares are? Houses. No, somebody, or maybe a big umbrella. But no, these are houses, right? And this green square, that's one of these houses that got pushed back. So it's not like they built it right on the road. And that green swath in the middle, that was a road that filled up with sand. Now here we are right after Katrina, which is only about a year after Ivan. So we have significantly more erosion. The beach never really recovered enough. A lot of red squares. And this is the overwash fan on the other side that you can see in this aerial image. What do we do after some of these as a federal policy? We go out and we dredge these overwash fans, pump them back up on the beach to keep the economy going in these areas. Going to get more and more expensive over time. And we'll see how long it lasts. But here's an example from more locally. This is Peggotty Beach, and from up on the North Shore area. And so this is water flowing across the barrier beach, taking sand, pushing it through, not caring about that car. When we talk about land subject to coastal storm flowage, you don't want to channelize flow, right? So between these houses, water is flowing faster because you have houses close together. Peggotty Beach up in Scituate. And it's just one of those rare examples of like almost after the storm, the winds died down and somebody was able to get out there with a drone and take these images. But just a nice example of overwash occurring. So that overwash and barrier beach migration has to move. Otherwise, all our beaches would have, died out on George's Bank. Things move over time. So they don't drown in place, they need to migrate, and to migrate they need to work their way up the shelf. Some of the evidence of that, here we are, some salt hay areas. Back in the 1700s, folks used to harvest salt hay. This is one of the carts, horse-drawn carts that was used. We have overwash, the entire system moving landward. And then now we're actually getting linear tracks. And we were wondering what those were, and then somebody found a hoof print in between them. So these are actually cart tracks from salt hay. And people weren't harvesting salt hay out here on the beach. It's because this habitat has rolled over and now is getting exposed on the frontal beach. Now, what happens when we have structures in the way, seawalls, revetments, that sort of thing? If we don't have them, then we're going to get landward migration of the beach, but there's an overall preservation of the beach width. If we have something here, our upland is protected, but it is at the cost of the natural resources, the dunes or beaches, whatever is seaward of that. Some examples of blocked perpendicular transport. Here's from town of Dennis. This is about a 1.3 mile revetment, a lot of private revetments along that shoreline. Here's the end of it, right? And here's one of the more popular beaches in the town of Dennis, a big economic driver for the town. You can see that this revetment has actually preserved the upland. These houses wouldn't be here if you extended that line across it. That said, at high tide, this water goes right up to the revetment. There's no beach. So it's a give and take. What's more important to the town? What's more important to the private property owner? There's definitely some conflicts in the coastal area to keep in mind. And when we're thinking about erosion, what is erosion? It's just one part of sediment transport. So we can see sediments being transported in this direction here, pretty obviously. But what's accretion? Accretion is more coming into an area than is leaving an area. Erosion's vice versa. And we can actually get dynamic equilibrium down here. So that just means you have as much coming in as going out. So it looks the same year to year. That doesn't mean there's not material moving. You could have a large volume of sand flowing through an area. But if it's just the same coming in as leaving, it looks the same year to year. It gets more complicated when you start adding cross shore to longshore. It gets even more complicated when you have erosion in the cross shore and accretion in the longshore. But all these parts are a sediment budget, right? So trying to figure out where the sediment's coming from, where it's going in any particular location. The Center for Coastal Studies put together a sediment budget. So here's those longshore net indicators I talked about. And here's an actual volumetric. So this is a two-dimensional and this is a three-dimensional. And what they showed is there's a nodal point, right? So that's where material is moving away in both directions. So it's an area that's eroding and it's providing material. Right around Thumpertown, in this kind of area, so you have material moving in that way and material moving that way. And then there's actual rates associated with that, how much material is moving in any particular direction, how much material is a sink, so that's an area that's accumulating sediment instead of eroding sediment. And that's, I believe that's either on the town website or somewhere available. So the idea is, can we live with erosion, right? So erosion is important because we wouldn't have dunes and beaches if we didn't have erosion. Some other parts of the country get a lot of their sand from rivers down from the mountains. That brings that material all the way down to the shoreline and distributes it around. We don't have those kinds of mountains and rivers on Cape Cod. We pretty much have to cannibalize what was put down by the glaciers. That has to get eroded in order to have this. Of course, that never makes anybody feel any better when it's their house. Nobody wants to hear that, you know, the sand under your house is going to coastal resource areas. So it's the public versus private competing interests. One thing to consider is everybody wants to live on Cape Cod. It's a wonderful place. I certainly enjoy it, but things have changed. Oh, that's me. I got to wrap it up so. So we have had significant storms in the past. The hurricane in 1945, hurricane 1954, Hurricane Carol, caused $15 million in crop damage. This is a historic aerial photograph from the Cape Cod Commission's chronology viewer. You can see these are some of the areas that were farms. They're not farms anymore. This is I mean, it's not that densely populated, but it's a lot more densely populated than it was in 1954. We're not going to have $15 million of crop damage. It's going to be in the billions of dollars of private property and homes. So what can we do to try to increase the resiliency of property on Cape Cod? Well, we need to look at various adaptation strategies. The first to think of is protection up at the top. And that's kind of the classic trying to build something to stop it, at least in the short term, whether it's a seawall, whether it's a revetment, even sand nourishment. These are all ways to try to protect property. If you do certain things like revetments, wherever you stop it, you may actually be making things worse. So you need to take into account what is the potential impact of that. And hopefully you're taking into account the sediment budgets when you plan these sort of structures. Another way is accommodation. Right? And the classic one for that is get out of the way. The water's coming. You're getting out of the way vertically. Increasing your freeboard might be an example of accommodating. So you might be able to, raise up out of that occasional floodwater. Another bucket of adaptation strategies is retreat, getting out of the way entirely. So if you had built your house on George's Bank 15,000 years ago, neither of these would have worked, right? That's not a viable option. We're usually not building our houses on the 1,000-year time scale, but, hundreds of years, certainly the hope, and we have houses on Cape Cod that are at least 200 or 300 years old. So trying to keep in mind the usable lifespan of the property is going to drive what kind of adaptation strategy. Additionally, can you find where all the stars align and you can do, No, I didn't put the word retreat on there. That's good. We don't like to use that word. I think it's managed relocation now because it makes people feel better. So here's an example where managed relocation actually worked. That we had an area, this is a parking lot in Brewster. That's the edge of the parking lot. It was seeing a lot of damage after storms. Very frequently, every year they were having to go out. You can see here's the natural dune behind where the parking lot is. That just shows how high that water was coming fairly consistently. You also had a revetment over here that may have been causing some additional damage to the adjacent property. So what they did was they actually pulled out this parking and replaced it with dune. So there we are. We have a smaller parking lot. They were able to move some of the parking up there. And when I say they pulled out the parking lot, if we think far enough back in time, this used to be a dune. They got paved to be a parking lot. So it's really a dune restoration, not a creation. But here we are kind of in the building phase, and then after they had some time to vegetate it, this is what we're looking at. So the idea here is, yes, this does erode, right? But it also builds back up. They haven't had to go out and completely fix the asphalt toe and pull chunks off the beach anymore. It's a little bit softer alternative that works more in line. Also, we can't really see this elevation change, but it doesn't allow the water to just flow through the parking lot and into some of these inland areas. So we're approaching the end. Just wanted to chat about the difference between adaptation and mitigation. So everybody knows what the impacts are, right? Hurricane Katrina, that was $148 billion storm. Sandy was a $71 billion storm. Very expensive to have impacts. Things you can try to reduce those impact costs. One is mitigation. And the idea with that is, a classic example is trying to reduce fossil fuels and greenhouse gases. Those are things that are going to take decades to show a result. They're also going to take more than just the town of Eastham to do it. You're going to need to get global agreement on this. The other thing you can do is adaptation. Adaptation is something the town of Eastham can do. This is trying to encourage, higher freeboard or zoning certain areas as, vulnerable. And the idea between mitigation and adaptation, I found this cartoon that I like. Mitigation is actually trying to solve the problem, right? Adaptation is just dealing with the problem as is. And neither one of these little lizards is going to be okay by himself. Because even if you're working to solve the problem, that water's still pretty hot. You're in trouble. And if you just adapt to it, you still have the flame on. So you still have the issue. So you really need to be doing both fronts to try to address the problem. And if it's purely cost, trying to make it the most economically efficient. And when we're talking cost, our choices matter and our choices make an economic difference. So For global action, this is mitigation again. If we can change the scenario, if we can change it from worst case scenario down to, intermediate scenario, we're still going to have 2 feet of sea level rise. We've bought into that. It's just when it's going to happen. If we can push that 2 feet off an extra 50 years, it's going to be a lot cheaper to adapt in the meantime. On that side, every adaptation dollar we spend, we've shown that we actually save $6. So it does make sense to plan and do these kinds of adaptation projects. An adaptation project might be, limited buyouts of areas or raising a road or something like that. So you do see economic impact over time. We haven't had enough time to go through, every possible answer for every possible question, but hopefully this gets some ideas in your head, and I think we still have some time for questions. The first.
I just wanted to make sure I understood what you were saying about revetments or seawalls. If the entire coastline were revetted, would that have, what effect would that have on the beaches?
So if the entire coastline were revetted, eventually we would have no beaches. We would have no dunes. So the idea is the shoreline used to be much further offshore. It's been allowed to erode over time. That material feeds down into the beaches and dunes. And one of the things I didn't talk about too much, but there's 2 main aspects. One is that a revetment or seawall is going to deny sediment to the system. So if you stop it from eroding, you're protecting the upland. But when you protect the upland, that material is not sand going onto the beach and dune. The other potential impact is wave reflection. So water just kind of gently flowing up the slope of a beach is going to expend its energy over a longer horizontal distance, whereas if it slaps against a seawall, it is high turbulence in a short horizontal distance that tends to mobilize sand, very basically makes erosion worse. And I guess in your example, we've bathtubed all of Cape Cod, but eventually if that revetment ends, you have potential terminal scour. So wherever you end it, you may be focusing energy. And you can focus it a couple of different ways. One, you can actually refract the waves around the end, where you're going to flank and kind of go behind that revetment. But 2, you can also set up currents along the structure. So if you had like a smooth seawall, water is going to flow against that based on certain wave angles, and eventually it's going to hit a spot where it's going to hit the natural bank or a dune, and that's downdrift. But even immediately in front of the revetment, you don't stop erosion, you can displace it. So if you are stopping the upland erosion, that probably means that somewhere downdrift is eroding, but also the fronting beach might get lower. So you're going to accelerate that beach erosion if you're stopping or really just displacing the upland erosion. Yep.
So we have all these revetments in this town, they're supposed to nourish. How much of an impact does the nourishment have? And does it make more sense to nourish at a particular time of the year versus a different?
Sure. So question about nourishment. A lot of towns now require nourishment if you were going to build a revetment or seawall to make up for that material that's being deprived of the system. So if you have a seawall that's, so long, you have a coastal bank that's so high, the erosion rate is so fast, you get a volume that you have to put down every year. And that's compensatory nourishment. That's to make up for the upland loss. That does have an effect. One of the issues we've seen is a lot of revetments, seawalls, jetties were built without that requirement. So Eastham actually has been pretty good about having that on a lot of the revetments. Some of the other areas I've seen, they may have, a mile of revetments without that. So when somebody wants a new revetment, they're putting in, 1% of what should be going onto that shoreline. So they're not really going to see much of an impact based on what they're doing because everybody else isn't doing it. If you have everybody doing it, it has the potential to offset what that erosion would have occurred. One thing it doesn't look at is moving into the future, our increased sea level rise. We didn't talk about it. It's called, the easiest way to think about it is something called the Bruins rule, that if you have a certain amount of vertical sea level rise, that correlates into a certain amount of horizontal erosion. So very basically, sea level's going up, erosion is going to increase. The rates are tied. So if you're increasing vertically faster than you have been, you would be increasing horizontally faster. So the old horizontal erosion rate is not necessarily going to hold going into the future. Let's see, some other things. The time of year. It depends. Everything's really site specific. But if you have a revetment that's already getting wet at high tide, it probably doesn't matter what time of year you do it. If you actually have some coastal resources in between the water and that revetment, then usually it's during a storm, right? So that's when natural erosion would have occurred. That the storm comes in, it displaces a bunch of that sand down onto the beach, and that actually trips the water and waves as it comes up for, impacts during that particular storm. It's really hard to do that. I have seen some really big projects like the Sconset project down on Nantucket, that they will stockpile sand kind of right above their geotube, which is a coastal engineering structure, and that's designed to erode during storms and come down. There's also a lot of other times where it's just kind of reflecting off the geotube, but the idea of additional input during a storm is good, but that's making up for wave reflection. If it's just compensatory nourishment, it doesn't necessarily matter what time of year it goes down. From a coastal processes point of view, that's not saying that various species aren't going to be very concerned about what the grade of the beach is during certain times of the year.
But you're saying that we should index the amount of nourishment to the sea level rise. Because you're saying that as it rises, that affects.
It certainly does affect it. I think now we're starting to get into what makes sense scientifically and logistically versus what may be fair and legally viable. So if you have a property that's, 100 feet deep, so from the top of the bank to the road is your property, and that's 100 feet. Once you've put in the amount of material that would have eroded all the way back to the road, should you be allowed to stop? Because that's all your material that would have been provided to begin with, and now it's the road. So that's one of the sticky points. A lot of the state guidance just looks at long-term rates, but does recommend looking at short-term rates. I don't really know of any guidance that talks about, potentially increased rates, but increased rates based on sea level rise can be difficult to do. One of the things I like to One of the things I like to recommend is triggers in addition to compensatory nourishment. So if you are putting in the amount that would be required to make up for the deprivation to the system, that's one thing. But if the beach is getting lower due to wave reflection, a variety of things, that means that it's not acting in a natural way anymore. So you can also put a trigger in saying, if the revetment has caused the beach to drop a foot, you have to put that much sand back in to get it back to that elevation. Triggers can be difficult at times because, again, if everybody along the shoreline isn't doing it, it gets really difficult because that one person is trying to make up for everybody else. So it's often a case of what's fair or reasonable versus what is best for the coastal resource area. Yep.
I live over by Boat Meadow, and in the past 2 years, I have seen tremendous erosion occur with the marshes in there. The river has changed, a lot of erosion has occurred in there. Now, is this because a lot of what we're talking about is sea level and greater storms coming in? I mean, it's significant. I mean, it really is. And I just kind of wondered down the road, are we going to see more of our marshes just disappearing, just being eroded out and disappearing out there?
So that'll be the next talk. We'll have that on. But no, it is a very complicated issue. So I mean, we have marshes that are vulnerable due to predation. You may have certain kind of crabs, invasive crabs that are coming in and causing it to calve off. You may be having higher groundwater. You may be.
The water level is where it's never been
Mhm.
before, which to me is sort of
Yeah,
startling, you know, 'cause I just see a lot of things happening with the water and the road.
absolutely. And you can also have groundwater. Last winter, we had some of the highest groundwater we've had in a long time. So when you have the groundwater coming up and the sea level coming up, you've got a lot of water in these estuaries. The estuaries are really valuable because they kind of act like a sponge when a storm occurs, that the water comes in and gets absorbed by the marsh, and then that's not as much water in the rest of the estuary. So they're very valuable. One of the things we look at to kind of how they deal with sea level rise is marshes need to migrate. They kind of need to go up that coastal plain. If they can't go up the coastal plain, they may be running against like a seawall, right? And they can't get up that. In addition to just seawalls, just steeper topography. So if you have a vertical change, that's going to be much greater across a very gentle slope than it is a very steep slope. So you're not getting as much marsh migration against a steep slope. And when you start seeing a lot of the high marsh go away and converting to low marsh, that might indicate that that marsh is kind of on its way out. That's one of the things that I'm working on with the Pleasant Bay Alliance, the Center for Coastal Studies, looking at a way to evaluate the marsh down in Pleasant Bay to see which areas may be vulnerable to sea level rise, what areas kind of are converting a lot of high marsh to low marsh, and then what kind of treatments might be available to try to extend the life of some of these marshes where some of the migration might occur. But no, it's a very important point that, I mean, things tend to act more, you know, they're simpler out on like the Atlantic shoreline when you just have sand moving and maybe some really steep banks, and it gets confusing because there's various different types of, you know, sediment in those banks. But once you start getting into marsh, you have biology involved as well, and it starts getting much more complex. But no, a very important point that, you know, it's not just the sand and the shoreline properties. When we start talking about those marshes, you start getting these floodplains extending way into town that they may not be. We're not waterfront, but when you start thinking about that floodplain, it extends up in there.
Crabs and that kind of thing and destroying the marshes themselves?
Oh yeah. There's some types of invasive crab that will come in, and usually you see that kind of caving off the sides versus an overall lowering of the marsh. But it's certainly one of the ways that marshes are impacted. And that's something we didn't even get into, potential invasive species migration up the coastline based on the warmer temperatures. We always looked to like, thank goodness that we finally had our first cold snap that the mosquitoes are gone. But that may be getting later and later in the years that global temperatures go up. Yeah, and I'll stick around after for a little bit if people have more questions.